So following the lead of what many books do, we'll finish up our treatment of fluids and elasticity by looking at the elasticity part of it. Specifically, what we'll be interested in is stress and strain. Now, personally, I've always found this sort of a strained inclusion into a chapter of a text. It's just that in most introductory physics texts, this is one or two sections, and it does tie together in that you can think of pressure as being a bulk stress. And so I guess you can go ahead and go with that. The other classic place it gets put is with statics, because deformation considerations can give you additional equations thinking about static equilibrium. But in any event, here we are. And so we'll go ahead and talk a bit about stress and strain. So thinking about, let's say I've mounted a rod to a wall like so. And then let's go ahead and say I pull on the rod with some force F. Now it will be the case that the wall will also have to pull on the rod with a force negative F, otherwise the rod would go flying. Now, so far we've been looking at the rigid body model where we just say, yeah, okay. But in reality, the rod's going to get a little bit longer, like so. So if originally the rod was length L, it will have grown by a length delta L. And similarly for compressions, if I compress this, we could talk about shrinking by delta L if we wanted to. Now, at the end of the day, we can go ahead and treat this all as if it were just so many cases of Hooke's law being applied here. So greatly exaggerated. I'm drawing a collection of the molecules that make up my rod. And so if I'm going to go ahead and pull on it, pull on the rod, what's going to happen is that all of my molecules, actually let's leave those in place there, all of my molecules will shift over a little bit in order for the rod to actually get longer. Now if we think about what that means for the bonds between adjacent atoms, in this case here, what we will call this a tensile stress. These bonds here don't get any longer, but this bond here does end up getting a bit longer. Same with this one, and so forth. So we can start to think about how much each bond gets stretched by. And so what we can think of is, can we come up with some sort of a proxy for the average extra force, or the average force that we apply on these molecules to stretch the bond a bit? And you can say, well, sure, I applied my force like so. And then what did I do? The force got split up over the atoms in this row, the atoms in this row, the atoms in this row, and so forth. And so if we think about our rod in 3D here, and I'm just going to make it a bar like so, we'll say that the area at the cross-sectional area here will be a good proxy for counting how many atoms I have in a plane. Okay. And then similarly, we can say, and what would be a good proxy for saying how much one of these atoms got stretched by? That would be to take the stretch of the whole thing and divide it by the original length. And then this will give me a percentage stretch of each atom like so. So we characterize the force being applied spread out over the area. We'll call this the stress. And in this example here, this is what we will call the tensile stress. And that's the F over A part of it. Some engineering books will use the symbol tau, but since we've already used tau for torque, I don't want to confuse things. Similarly, this delta L over L, which is our proxy for how much has the average bond gotten lengthened, this is a strain. In this case, this is what we would call a tensile strain. Now, the proportionality that's going to tie together the stress and the strain is going to depend on the details of the crystal structure of the material and the details of the bond structure within the material. So we bury all of that into a thing that we call the modulus. In this case here, it'll be known as Young's modulus. And if you're wondering, is that the same Young that suggested that, at least in certain cases, like for proper names and such, ancient Egyptian hieroglyphics could actually encoded sounds? You would be correct. It's the same guy. He got around a lot. So if we go ahead and pull on this, this is an example of a tensile stress. The stretch, the percentage stretch, it would be the tensile strain, and then this is Young's modulus. And just for reference, some engineering books will call Young's modulus E. Basically, no physics book will ever do that because of the confusion with energy. So this will, 10 tensile stress. There we go. And it turns out there's a couple other ways that we can deform objects, and we'll be able to write similar stress equals modulus times strain relationships for each of them as well. However, it's worth spending and I think it's worth spending just a second here to say that for all of these things, there will be a curve that sort of looks like this, where if I plot the stress against the strain, there'll be a region that's pretty linear, and then usually curves off a little bit at the end. This gets called the elastic region. And then I'm going to draw a dot here. This will be what's called the elastic limit. So this is a region where if I give it a stress and then let it go, it'll return back to its original shape. Here, permanent deformation will occur. And then this last point here gets called the breaking point. Since it's easier to discuss this in terms of a shear stress, that's the one I'm going to go ahead and do next. A lot of physics books drop this, but I think it's instructive for being able to think about this. So let's go take a look at a shear stress. So prototypical case for shear stress will be, we'll take our same bar like so. There we go. Mount it, but now we'll mount it to the floor. And we will go ahead and apply a force like this. And the bracket here would have to apply a force in the opposite direction like that, or else the whole thing would go flying. All right, so now we'll still be able to write a stress and a strain thing, and again, it's going to be this area here that counts, But now what's going to happen is we're going to deflect the whole bar sideways, like this. And so we'll say that this greatly exaggerated here, we'll call this sideways displacement here delta x, like so. So then my shear stress, and we'll still say the length of my rod is L. And I want to be clear here that unless the material is jello, in typical situations, the shear stress is going to not be a huge number. Jello being the classic example. If you've ever played with a block of jello and flicked the top of it, congratulations. You exerted a shear stress to it, and then the shear strain would be significant on it. So anyway, we can describe our shear strain with delta x over L. So this is my shear strain. And my shear stress is still going to be F over A. And why does that work? Well, here, let me fill in the modulus here. So this is my shear stress. And then this gets called the shear modulus. Modulus. There we go. So now why does it still work that way? Well, if we go and look at this atom on atom, like so. Let's move it down to the next page. There we go. So if we go ahead and look at atom by atom, let me just draw in a few more atoms like so. When I apply a shear stress, the displacements are going to look something like this. And so it's still, what green was I was using? So it's still these bonds here that are getting lengthened out. And as long as the material isn't jello, these angles are so teeny tiny that you can basically say that the distance that the bond gets stretched is proportional to the sideways displacement of the bar. So that's why you're justified in doing that. Now, the reason I bring this up is that this also starts to explain the elastic limit. So just let's say I give it a heck of a lot more shear. So let me just go and put in the initial positions of my atoms. And now let's say I do a much more substantial shear. Maybe it starts looking like this. Well, in this case here, and then we can, oops, let me put, maybe it starts looking something like that. So in this case here, this bond is stretched like crazy. And it'll actually become energetically favorable to break that bond and instead bond with the new neighbor that's actually now physically closer. And the same sort of thing happens all the way up the material. And so since you've changed the bond structure of the material, you'll have changed the shape. So you can do a similar kind of argument, although it's more tedious for tensile stress because you have to start taking into account that the material gets skinnier as you keep tugging on it. But I think it's easiest to understand in the context of a shear stress. So then finally, to just conclude our possibilities, there is one more possibility that is widely considered. And this is what's called a bulk stress. Now, in a bulk stress, what you do is say if this is my material, And we'll just say, to make it simple, it's A on all sides. If I exert a uniform force F in all directions like this, what's going to happen is we're going to force all the bonds to get closer together. So in this case here, the bulk strain is going to be delta V over V. And usually people throw in a minus sign here because under a bulk strain, my object is going to get smaller. And since they like to keep the stresses as positive numbers, but my delta V is negative, usually they stick in a minus sign like so. And I go ahead and call that one, they write as a negative B. Again, some engineering books will call this K. So sorry, here, let me just say bulk modulus. So some engineering books will call this K, but again, no physics book will because of the confusion with kinetic energy. And so then we will say F over A. And in this case here, a good typical situation would be something like you're worried about chucking a piece of material like, I don't know, a submarine or something underwater. So a lot of times you'll just say this is the pressure, like that. And so you'll notice here with all of our stresses, so this is a bulk stress. With all of our stresses, the answer newtons per square meter, or pascals. All of our strains are dimensionless. And our moduli then also have units of newtons per square meter, which are pascals. Good rule of thumb, again with the exception of Jello, being sort of a notorious case of something that's particularly squishy. The most moduli for practical engineering materials, and I'm talking bulk modulus, Young's modulus, shear modulus, doesn't really matter. They'll all be on the order of a few hundred gigapascals. Remember, the giga prefix means times 10 to the 9, or billion. So just to do one quick example of this. So let's just say I went ahead and tossed a block of iron underwater. Iron underwater. And we'll say that it, or actually I won't say underwater. I'll just say I compress a block of iron. And we're going to have to use a rig here that involves hydraulic oil with 200,000 psi of pressure. What I would like to know is what is the percentage change in volume? Well, 200,000 psi you can work out is 1400 is 1.4 gigapascals. So we'll just use that. So then we can go ahead and say that the pressure is equal to minus B delta V over V. And so delta V over V will be equal to minus P over the bulk modulus. So this will be 1.4 gigapascals. And a typical number for iron is something like 162.7 gigapascals. It depends on the alloy, it depends on the crystal structure, etc. But just to give you some sense of this, and so you can see that this is a little less than 1%. It's going to be minus 0.0086. So about it will compress by 0.86%. All right, that will do it there. So we'll go ahead and catch you in the next set of videos.